Tonight we drift into the quiet mysteries of the universe. You don't need to follow every word. Just let the story carry you like starlight across a calm sky. In these moments, as your breathing slows and your thoughts begin to settle, we'll explore the gentle science of fire, of light, of the warmth that connects us to the cosmos. There is no hurry here, no test to pass, only the soft unfolding of understanding, as natural as the spreading of dawn across a silent horizon. Let these words be like a gentle river, carrying you wherever you need to go, sir, whether toward thoughtful contemplation or peaceful rest. Imagine, if you will, a room growing dark as evening settles. The curtains drawn, the world outside fading into blue shadow, and in this quietness a small gesture, the striking of a match, the touch of flame to wick, and suddenly there exists a tiny sun in the darkness. A candle flame, no larger than the pad of your thumb, yet containing within it stories as old as the universe itself. Watch how it dances, this little heartbeat of light, how it sways to currents you cannot see, responding to the subtlest movements of air around it. There is something mesmerizing in its gentle motion, something that speaks to the deepest parts of us, those ancient corners of our minds that remember when fire was our first companion against the night. The flame rises and falls, stretches and contracts. It breathes in its way, consuming the oxygen around it in a slow, steady rhythm that matches your own breathing if you pay attention long enough. The base of the flame rests close to the wick, a cooler blue that gradually warms into gold and amber as it reaches upward. At its edges, the flame becomes transparent, almost invisible, before dissolving into the darkness. It is never still, never fixed, always changing yet somehow always the same. Like thoughts drifting through a quiet mind, the flame exists in a state of constant, peaceful becoming. In the soft illumination, shadows gather and retreat across the walls. They move like memories across the face of consciousness, now sharp, now fading, now reappearing in new forms. There is a story being told in this interplay of light and dark, a wordless narrative as old as time itself. For as long as humans have existed, we have gathered around flames like this one, watching their dance, finding in their warm light both physical comfort and something less tangible. A focal point for contemplation, for connection, for the quieting of restless thoughts. Notice how your eyes are drawn to the flame, how it holds your attention without demanding it. There is a natural sympathy between our consciousness and this ancient phenomenon. Perhaps it is because we recognize in fire something of ourselves, a brief, beautiful coalescence of energy, a temporary pattern in the flow of the universe. Or perhaps it is simply that in the flame's gentle movement, our minds find a rhythm that soothes the electric bustle of daily thought, allowing us to sink into a deeper, slower awareness. The candle burns, consuming itself as it gives light. The wax melts, flows downward, and resolidifies. A small cycle of transformation mirroring greater cycles in nature. If you listen closely, you might even hear the faintest whisper as the flame breathes, a soft sound like distant tide on sand. This is the voice of combustion, of carbon and hydrogen embracing oxygen, in a dance as old as Earth's atmosphere. A chemical poetry written in light and heat rather than words. As you watch the flame, consider how this simple phenomenon connects you to humans throughout time. Thousands of years ago, someone just like you might have sat before a fire, watching the same dance of light, feeling the same warmth, thinking thoughts not so different from your own. The technology has changed, from open fires to candles to electric lights, but the fundamental relationship remains. We are still beings of carbon drawn to this release of energy, this momentary reversal of entropy that pushes back the cold and dark. The candle burns steadily now, having found its rhythm. The flame stands taller, more confident, as if it has remembered its purpose. Around it, the air circulates in invisible currents, feeding the fire, carrying away its warmth in widening ripples. Energy flows outward, touching first the nearby air, then the walls of the room, and eventually dispersing into the greater world beyond. Nothing is lost, merely transformed, redistributed. The light that reaches your eyes began as chemical energy stored in the wax, itself captured from ancient sunlight by plants long ago, preserved through vast stretches of time until this moment of release. As the evening deepens around you, allow yourself to be present with this small miracle of physics and chemistry. There is no need to analyze or categorize every aspect of what you see. Sometimes the deepest understanding comes not from dissection, but from patient observation, from allowing the phenomenon to speak for itself in its own language of light and movement. The flame has much to teach, if we approach it with quiet attention rather than demanding answers. It reminds us that beauty and science are not separate realms, but different perspectives on the same reality. Like viewing a diamond from different angles, each revealing new patterns of refracted light. Now, as the candle continues its gentle burning, let us expand our view beyond this single flame, beyond this room, beyond this moment. For the story of fire is also the story of the cosmos itself, written across billions of years and unimaginable distances. The same principles that govern this humble candle also govern the great furnaces of stars, the explosions of supernovae, the subtle warming of planets by their suns. All are expressions of the same fundamental processes, the same universal laws, playing out at different scales. Long before there were candles, before there were humans to light them, before there was an earth to stand upon, there was fire of a different kind. In the beginning, though beginning may not be quite the right word for something that transcends our ordinary understanding of time, the entire universe was something like a flame. Not a flame as we know it, requiring fuel and oxygen, but a state of energy so concentrated, so intense, that it defies comparison with anything in our everyday experience. Imagine, if you can, all that exists in every galaxy, every star, every planet, every atom that will ever form, including those that will one day become your body, compressed into a space smaller than the period at the end of this sentence. Not just compressed, but transformed into pure energy, a singularity of potential, where the familiar laws of physics as we understand them reach their limits. This was the state of the universe before what we now call the Big Bang. Though that name suggests an explosion in space, when in reality, it was an expansion of space itself. About 13.8 billion years ago, this singularity began to expand. Not into existing space, for there was no outside to expand into, but creating space as it grew. In the first fraction of a second, a time so short that to call it instantaneous would be to vastly overstate its duration, the universe expanded from that infinitesimal point to a size many times larger, though still tiny by today's standards. This period, known as cosmic inflation, set the stage for everything that would follow. As the newborn universe expanded, it also cooled, much as the air from your breath becomes visible when exhaled into winter cold. This cooling allowed energy to condense into matter, first as elementary particles like quarks, then as protons and neutrons, and eventually as the nuclei of the lightest elements, hydrogen, helium, and traces of lithium. The universe at this stage was a vast, hot plasma, opaque to light, more like the interior of a star than the transparent cosmos we know today. For hundreds of thousands of years, the universe remained in this state, gradually cooling but still too energetic for atoms to fully form. Then, approximately 380,000 years after the Big Bang, the temperature fell enough for electrons to be captured by nuclei, forming the first complete atoms. This moment, known as recombination, transformed the universe from an opaque plasma to a transparent gas. For the first time, light could travel freely through space, and the cosmic background radiation, the afterglow of creation itself, was released. This radiation still permeates the universe today, having cooled over billions of years, to just 2.7 degrees above absolute zero. When we detect it with our instruments, we are literally seeing the echo of the universe's birth, the oldest light in existence. It surrounds us even now, passing through the room where you sit, a gentle whisper of cosmic history that connects us directly to those first moments of creation. As the universe continued to expand and cool, gravity began to exert its influence on the nearly uniform distribution of matter. Regions with slightly higher density attracted more matter, gradually forming the seeds of the cosmic structure we observe today. Over millions of years, these slight irregularities grew into vast clouds of hydrogen and helium gas, slowly collapsing under their own gravity. As they contracted, their centers heated up, much like the air in a bicycle pump warms when compressed. Eventually, the temperature and pressure at the core of these gas clouds became so extreme that hydrogen nuclei could overcome their mutual repulsion and fuse together, releasing enormous amounts of energy in the process. With this, the first stars were born. Cosmic furnaces that would transmute the simple elements of the early universe into the more complex ones needed for planets, for oceans, for life itself. These first stars were giants, far larger and brighter than our Sun, burning hot and fast through their fuel. Within a few million years, a mere moment in cosmic timescales, the largest of them exhausted their hydrogen and began to fuse heavier elements in their cores. This process continued until iron was reached, an element whose fusion consumes rather than releases energy. With their outward pressure suddenly removed, these massive stars collapsed and then rebounded in spectacular explosions called supernovae, scattering their newly forged elements across space. It is in these stellar deaths that elements essential to our existence were created. Carbon for organic molecules, oxygen for water and breath, calcium for bones, iron for blood. The atoms that make up your body, that form the candle and its flame, were forged in the hearts of stars long vanished. As the astronomer Carl Sagan once observed, we are quite literally made of star stuff. The debris from these early supernovae enriched the interstellar medium, providing the raw materials for new generations of stars and, eventually, for planets. Our own solar system formed approximately 4.6 billion years ago from such enriched matter, a swirling disk of gas and dust that gradually condensed under gravity's patient hand. At the center, pressure and temperature rose until hydrogen fusion ignited, giving birth to our Sun, a middle-aged, medium-sized star of no particular distinction, except that it happens to nurture the only world we know to host life. Around this newborn star, smaller eddies in the disk gathered material that would eventually form the planets. In the inner regions, where temperatures were highest, only materials with high melting points could remain solid, metals and rocky compounds that would form the terrestrial planets, Mercury, Venus, Earth, and Mars. Further out, beyond what astronomers call the frost line, volatile compounds like water, methane, and ammonia could condense into ices, contributing to the formation of the gas giants and their moons. Earth took shape through a process of accretion as countless impacts added to its mass. The largest of these collisions, with a Mars-sized body scientists have named Theia, ejected enough material to form our moon and likely gave Earth its tilted axis, which gives us our seasons. For millions of years after its formation, our planet was a hellscape of molten rock, constantly reshaped by impacts and volcanic activity. There was no solid ground, no water, no atmosphere, as we would recognize it today. As Earth gradually cooled, heavier elements sank toward the center, creating a layered structure with an iron-rich core surrounded by a mantle of silicate rocks. The lightest components rose to the surface, forming a thin crust and the beginnings of an atmosphere, though one very different from the air we breathe today. This early atmosphere, composed mainly of water vapor, carbon dioxide and nitrogen, with virtually no free oxygen, would have been toxic to most modern life forms. The young Earth's surface temperature was maintained above the boiling point of water for millions of years, until gradually the planet cooled enough for water vapor to condense. Rain fell, not for days or months, but for centuries, filling the lowest-lying areas of the crust and creating the first oceans. Within these waters, under an alien sky lit by a somewhat dimmer sun, the complex chemistry that would eventually lead to life began to unfold. It is here that the story of fire on Earth truly begins. For fire as we know it, the combustion of organic matter in oxygen, could not exist until two crucial ingredients were present: fuel and an oxygen-rich atmosphere. The early Earth had neither. The transformation of our planet from a water world with a reducing atmosphere to one capable of supporting flames is one of the most remarkable chapters in Earth's history. A story written by the smallest of living things. The first life forms, arising perhaps 3.8 billion years ago, were simple, single-celled organisms that extracted energy not through photosynthesis or respiration, but through chemical reactions involving compounds like hydrogen sulfide. These prokaryotes, similar to modern archaea, thrived in the oxygen-poor environment of early Earth, their metabolic processes actually producing carbon dioxide rather than consuming it. For hundreds of millions of years, life remained in this simple state, invisible to the naked eye, yet already beginning to reshape the chemistry of the planet. Around 3 billion years ago, a revolutionary new form of metabolism evolved, photosynthesis. Initially, these early photosynthesizers did not produce oxygen as a byproduct. Instead, they used compounds like hydrogen sulfide as electron donors in their photosynthetic processes. But eventually, perhaps around 2.4 billion years ago, cyanobacteria, sometimes called blue-green algae, developed the ability to split water molecules, using the hydrogen to build sugars and releasing oxygen as a waste product. This innovation triggered what scientists call the Great Oxygenation Event, a gradual but profound transformation of Earth's atmosphere. At first, the oxygen produced by cyanobacteria was quickly consumed by reactions with dissolved iron and other reduced compounds in the oceans and exposed rocks. But eventually, these oxygen sinks became saturated, and free oxygen began to accumulate in the atmosphere. For many of the anaerobic organisms that had dominated Earth for 1 billion years, this oxygen was toxic. They retreated to oxygen-poor environments, or perished in what might be considered the planet's first mass extinction. But for the evolution of more complex life, and for the possibility of fire, this oxygen was essential. By about 600 million years ago, atmospheric oxygen levels had risen to perhaps 10% of present levels, sufficient to support the development of multicellular animals. The stage was now set for the possibility of fire, though one more ingredient was still missing, a substantial amount of plant material to serve as fuel. The colonization of land by plants began in earnest around 470 million years ago. These early land plants, more similar to modern mosses and liverworts than to trees, gradually evolved the structural compounds, particularly lignin, that would allow them to grow upright and support themselves against gravity. Lignin, as it happens, is not only a structural molecule, but also an energy-rich one, perfect as fuel for fire once dried. By the Carboniferous period, which began about 360 million years ago, vast forests covered much of the land, and atmospheric oxygen levels reached as high as 35%, significantly higher than the 21% we breathe today. Under these conditions, even damp vegetation could burn, and fires would have spread more rapidly and burned hotter than in our current atmosphere. It is from this period that we get much of our coal deposits, formed when the lush vegetation of these forests was buried before it could fully decompose. The first wildfires on Earth may have been ignited by lightning strikes or volcanic activity as early as 420 million years ago, though the fossil charcoal record becomes much more abundant from the Carboniferous onward. These early fires would have played an important ecological role, clearing undergrowth, returning nutrients to the soil, and even stimulating the germination of certain seeds. Fire had become an integral part of Earth's systems long before humans arrived to harness it. The story of how our ancestors first controlled fire is largely lost to prehistory, though archaeological evidence suggests that Homo erectus may have used fire as early as 1.8 million years ago. The deliberate, habitual use of fire is evident by at least 400,000 years ago, with hearths becoming a common feature at human habitation sites. This mastery of fire represented a pivotal moment in human evolution, allowing our ancestors to cook food, increasing its nutritional value, stay warm in colder climates, deter predators, and extend the day's activities into the night. Fire also changed us biologically. The ability to cook food likely contributed to the reduction in jaw and tooth size seen in the fossil record, as well as to the expansion of the human brain, which requires substantial energy to develop and operate. The social gathering around a communal hearth may have stimulated language development and strengthened community bonds. In a very real sense, humanity as we know it was forged in the light and warmth of controlled flames. From those early hearths to the candle that burns before you now, the human relationship with fire has evolved into ever more sophisticated forms. The basic principles remain the same: fuel, oxygen, and heat combining in a self-sustaining reaction that releases energy, but our understanding and applications of these principles have grown immeasurably. That understanding begins with light, the most immediately apparent product of fire. Every flame you've ever seen, from the humblest candle to the grandest bonfire, communicates with you through the language of photons, particles, or waves of electromagnetic energy that travel from the source to your eyes at the universal speed limit of approximately 186,000 miles per second. The light from a flame is produced by several mechanisms. First, the heat of combustion excites atoms and molecules, raising their electrons to higher energy levels. When these electrons return to lower energy states, they release the excess energy as photons. The specific wavelengths and thus colors of these photons depend on the atoms and molecules involved and their energy transitions. In a candle flame, the primary light source is not actually the flame itself, but tiny particles of carbon, soot, that are heated to incandescence. As the wax melts and is drawn up the wick through capillary action, it vaporizes due to the heat. These hydrocarbon molecules break down in the flame's oxygen-poor interior, creating carbon particles. As these particles rise through the flame, they heat up and glow, producing the characteristic yellow-orange light we associate with candles and other flames fueled by hydrocarbons. This process is essentially the same as that which occurs in stars, though at vastly different temperatures and pressures. In both cases, matter heated to the point of incandescence emits electromagnetic radiation, with the spectrum of that radiation determined by temperature. A candle flame at around 1000 degrees Celsius at its hottest point glows yellow-orange. Our Sun, with a surface temperature of about 5500 degrees Celsius, appears yellowish-white. The hottest stars, at over 30,000 degrees, shine with a blue-white intensity. When you gaze at a candle flame, the light entering your eyes has been created through processes fundamentally similar to those that generated the starlight, that left distant suns thousands or millions of years ago. The photons themselves, once created, travel their path to your retina in essentially the same way, regardless of their origin. There is a profound connection here, a continuity of physical law that links the humblest terrestrial flame to the most massive stellar furnaces, but the light from a flame tells us more than just a story of atomic excitement and electromagnetic radiation. It also reveals temperature gradients, airflow patterns, and the chemistry of combustion. Look closely at a candle flame, and you'll notice that it's not uniformly colored. At its base, near the wick, the flame often appears blue. This is where complete combustion is occurring, where the fuel and oxygen mix in ideal proportions and at high temperature, producing a hotter flame that emits more blue wavelengths. Above this blue region, the flame transitions to yellow, orange, and sometimes even a reddish hue at its upper edges. These color variations map directly to temperature differences within the flame. The blue base may reach temperatures around 1400 degrees Celsius, while the yellow-orange regions are cooler, perhaps 1000 degrees, and the reddish tips cooler still, around 800 degrees. This temperature gradient creates what scientists call a blackbody radiation spectrum. Any object heated to sufficient temperature will emit electromagnetic radiation, with the peak wavelength of that radiation shifting toward shorter wavelengths, toward the blue and violet end of the visible spectrum, as temperature increases. This relationship, known as Wien's displacement law, applies equally to candle flames, molten metal, and stars. The colors we see in a flame are thus a direct visualization of energy states, a color-coded temperature map that our eyes can read intuitively. When prehistoric humans gathered around their fires, they were unknowingly observing a demonstration of quantum physics and electromagnetic theory, watching as energy transitioned between states in a dance of light and heat. That dance continues beyond the visible spectrum. A flame emits not only the light we can see, but also infrared radiation, which we feel as heat, and in smaller amounts, ultraviolet radiation. Our eyes evolved to detect the visible portion of the electromagnetic spectrum because that's where our sun's emission peaks, but the full language of light extends far beyond what we can directly perceive. Modern instruments allow us to analyze the complete spectral signature of a flame, revealing details about its chemical composition that would be invisible to the naked eye. Each element and compound, when excited, emits light at characteristic wavelengths, a kind of atomic fingerprint that scientists can use to identify the components of distant stars as readily as they can analyze the chemistry of a laboratory flame. When astronomers point their spectroscopes at stars, they are reading the light in much the same way you might intuitively read the colors of a candle flame. The absorption and emission lines they detect tell them about the elements present in the star, its temperature, its motion relative to Earth, and even the presence of planets orbiting it. All of this information comes to us in the language of light, a universal code that works the same way whether deciphering the message of a candle or a quasar. As you continue to observe the candle flame, notice how its colors shift and flow. The yellow-orange that dominates the visible flame is primarily due to incandescent carbon particles, as we've discussed. But at the very edge of the flame, where it meets the surrounding air, you might see a faint blue fringe. This is where complete combustion occurs, where carbon particles fully oxidize to carbon dioxide. The most efficient flames, like those in a well-tuned gas stove, appear almost entirely blue because they achieve nearly complete combustion. The familiar yellow of a candle flame indicates incomplete combustion, a process that produces both the warm light we find so appealing and, less desirably, some amount of soot and carbon monoxide. This is why candles can blacken ceilings when burned in large numbers, leaving a record of their incomplete combustion written in carbon. There's a wonderful balance here, a kind of cosmic irony. The very inefficiency of a candle flame, its failure to completely combust its fuel, is what gives it the warm, golden quality we find so soothing. A perfectly efficient blue flame, while hotter and cleaner, lacks the visual softness, the gentle fluctuation, the familiar comfort of a traditional yellow flame. Sometimes it seems imperfection has its own beauty, its own purpose. This interplay of efficiency and aesthetics, of physical process and perceptual experience, reminds us that even the most objective scientific understanding of a phenomenon like fire doesn't capture its full significance. The meaning of flame for humans extends beyond its chemistry and physics into realms of psychology, culture, and even spirituality. Consider how the light from a flame affects our circadian rhythms and mental states. Unlike the blue-rich light of electronic screens, which can disrupt melatonin production and interfere with sleep, the orange-yellow light of a flame mimics the spectral quality of sunset, potentially helping to prepare our bodies and minds for rest. There's a reason why candlelit dinners feel intimate and relaxing, why firelight seems to slow the pace of an evening, creating space for conversation and contemplation. This calming effect has likely been part of the human experience of fire since our earliest encounters with it. Imagine our ancestors gathered around their hearths as darkness fell, the warm light of the flames creating a circle of safety and community in a world where night brought very real dangers. The psychological comfort of fire may be as deeply embedded in our nervous systems as our physiological responses to its heat and light. As the candle continues to burn, observe how the flame responds to subtle air currents, bending, stretching, sometimes flickering rapidly and other times standing tall and steady. This sensitivity to its environment makes each flame unique, a never-repeating pattern that somehow maintains its essential identity despite constant change. Like the famous ship of Theseus that remained the same vessel, even as every board and nail was gradually replaced, a flame persists as a recognizable entity despite the fact that the actual matter composing it is continuously refreshed. The responsive dance of a flame illustrates a fundamental principle that extends far beyond combustion, the interplay between pattern and process. A flame is not a thing but a happening, not a noun but a verb. It exists as a pattern of energy flow, a structured process that maintains itself by continuously drawing in new material and releasing transformed products. In this way, it shares essential characteristics with living systems, which also maintain their organization through constant material exchange with their environments. This perspective, seeing the world in terms of processes rather than static objects, has profound implications for how we understand not just flames but all dynamic systems, from weather patterns to ecosystems to consciousness itself. Modern physics increasingly describes reality in terms of events and relationships rather than substances, a view that resonates with both ancient Eastern philosophies and contemporary systems thinking. As night deepens around the candle, its flame appears to grow brighter, in contrast to the surrounding darkness. This is partly a perceptual effect. Our pupils dilate in the low light, admitting more of the flame's radiance, but it also reflects the reality that a flame's visibility depends on context. In bright sunlight, a candle flame might be nearly invisible. In complete darkness, it can illuminate an entire room. This relationship between figure and ground, signal and context, reminds us that meaning often emerges not from absolute qualities, but from relationships and differences. The flame means more in darkness, just as a musical note takes its significance from its place within a melody or a word from its position in a sentence. Context shapes content in ways both subtle and profound. If you've been watching the candle for some time now, you may have noticed slight changes in the flame's height or brightness as the wax is gradually consumed. This too tells a story of energy stored and released, of transformation and impermanence. The solid wax, which seems so stable and unchanging, is actually in a continuous state of becoming, converting from solid to liquid to vapor to light and heat, participating in cycles of matter and energy that extend far beyond this single moment of illumination. The physics of this transformation connects the humble candle to the grandest cosmic processes. The wax, derived ultimately from plants that captured solar energy through photosynthesis, contains carbon-hydrogen bonds forged using the energy of sunlight. When these bonds break during combustion, that stored solar energy is released as heat and light, a delayed echo of sunshine that fell on Earth months or years, or even, in the case of fossil fuels, millions of years ago. This is the deeper truth of all fires on Earth. They are the release of captured sunlight. Whether we burn wood from a tree that grew over decades, candle wax rendered from plants or petroleum, or fossil fuels formed over geological epochs, we are tapping into energy that originated in the thermonuclear fusion at the heart of our star. Fire in this sense is sunlight unwinding, solar energy returning to its radiant form after being briefly trapped in chemical bonds. And what powers the sun itself? The same fundamental force that ultimately drives nearly all processes in our corner of the universe: gravity. It was gravity that compressed the solar nebula until hydrogen atoms in the core were forced close enough together to fuse, releasing the energy that would radiate outward to warm a family of planets. Gravity continues this work today, maintaining the pressure at the sun's core that allows fusion to continue at a steady rate, providing the reliable energy flow that makes life on Earth possible. From gravity to nuclear fusion to sunlight, to photosynthesis to combustion, to the warm glow that now illuminates these words, this is the lineage of energy that connects the candle flame to cosmic processes spanning billions of years and unimaginable distances. When you observe a simple flame, you are witnessing not just a local chemical reaction, but a link in a chain of energy transformation that extends to the very origins of our solar system. As the evening progresses and the candle burns lower, you might notice subtle changes in how the flame behaves. Perhaps it grows smaller, or begins to flicker more as the wick shortens, and the supply of melted wax becomes less consistent. These changes remind us that all flames, like all processes in our universe, exist in time. They have beginnings, middles, and endings, though what appears as an ending at one scale might be merely a transformation when viewed from another perspective. The concept of time itself is intimately connected with energy and its transformations. In thermodynamic terms, time's arrow points in the direction of increasing entropy, from states of concentrated, usable energy toward states of more evenly distributed, less available energy. A freshly lit candle represents a state of relatively low entropy, with energy concentrated in the chemical bonds of the wax. As it burns, this energy disperses into the environment as heat and light, increasing the overall entropy of the system. This one-way flow from order to disorder, from concentration to dispersion, gives time its apparent directionality. We never observe the reverse process, scattered heat spontaneously concentrating itself back into a candle, or smoke and carbon dioxide recombining to form wax. Such a reversal would violate the second law of thermodynamics, which states that the total entropy of an isolated system always increases over time. Yet this inevitable march toward greater entropy doesn't preclude the temporary, local creation of order and structure. Living organisms, for instance, maintain and even increase their internal organization by consuming energy from their environment and exporting entropy. A growing plant creates the highly ordered structure of its cells and tissues by capturing the energy of sunlight and releasing heat to its surroundings. Similarly, human civilizations create complex technologies and social structures by tapping into energy sources, initially human and animal muscle, later wood and coal and oil, and increasingly renewable forms of solar energy. A flame, in its way, bridges the gap between order and chaos. It displays remarkable structure. The distinct zones of a candle flame are far from random, yet this structure exists only as a temporary pattern in the flow of energy from concentrated to dispersed forms. The flame is a structured, dissipative system, maintaining its organization not despite but because of the energy flowing through it. This balance between structure and flow, between pattern and process, appears throughout nature at every scale. From the spiral arms of galaxies to the intricate forms of snowflakes, from the branching patterns of rivers and trees to the complex dynamics of weather systems, we find systems that maintain their form through constant material exchange with their surroundings. The flame on your candle participates in this same fundamental dynamic, a humble yet perfect exemplar of principles that govern the cosmos. As we contemplate these connections between the microcosm of a single flame and the macrocosm of universal processes, consider too the flame that burns within your own body. Not a literal fire, of course, but a metabolic process that shares key characteristics with combustion. Your cells continuously combine glucose with oxygen, releasing energy that powers every aspect of your physical existence, from the beating of your heart to the thoughts forming in your mind as you read these words. This cellular respiration is, in chemical terms, a controlled form of burning. Glucose, C6H12O6, combines with oxygen, O2, to produce carbon dioxide, CO2, water, H2O, and energy in the form of ATP, adenosine triphosphate. The E-balanced equation is strikingly similar to that of a candle burning, though the biological process occurs at much lower temperatures and with greater efficiency, thanks to enzymes that facilitate each step of the reaction. The parallels go deeper still. Just as a flame requires continuous input of fuel and oxygen, your cells depend on a constant supply of glucose and oxygen delivered through the circulatory system. Just as a flame produces waste products that must be carried away, your cells generate carbon dioxide that must be transported to the lungs for expulsion. And just as a flame generates heat and light, your metabolism generates body heat and, in some organisms like fireflies and certain deep-sea creatures, even bioluminescence, living light. There is a certain poetry in the fact that the same basic process that warms us from without also energizes us from within. We are, in a very real sense, slow-burning fires ourselves, our bodies maintaining a carefully regulated combustion that typically lasts for decades rather than the hours of a candle or the minutes of a match. The flame of human metabolism burns at approximately 98.6 degrees Fahrenheit, 37 degrees Celsius, a temperature that represents a compromise between chemical efficiency and biological stability. This internal flame connects us metabolically to all other aerobic life forms, from the tiniest bacteria to the largest whales. All of us are burning the same basic fuels through similar chemical pathways, all converting the energy stored in carbon compounds into the motion and maintenance of life. This shared energetic foundation underlies the stunning diversity of living, forms a reminder that unity and variety are not opposing principles but complementary aspects of natural systems. Our metabolic fire also links us back to the cosmic story we explored earlier. The glucose our cells burn comes ultimately from plants that captured the energy of sunlight through photosynthesis. The oxygen we breathe was released by those same plants as they split water molecules to obtain hydrogen for building sugars. Both the fuel and the oxidizer that power our internal flames are products of photosynthesis, which itself depends on the steady radiance of our star. When you feel the warmth of your own body, you are feeling, in a very direct way, the warmth of the sun. The energy flowing through your veins and neurons began as hydrogen fusing to form helium in the solar core, traveled across 93 million miles of space as photons, was captured by chlorophyll molecules in plant leaves, stored in the chemical bonds of carbohydrates, and finally released within your cells to power your existence. You are quite literally animated by starlight. This realization that the boundaries between out there and in here are more permeable than they might first appear invites a shift in perspective. The flame of a candle, the flame of the sun, the flame of your metabolism. These are not separate phenomena, but variations on a theme, different expressions of the same fundamental processes of energy transformation that pervade our universe. As the candle burns lower, its flame casting longer shadows across the room, let's turn our attention to another aspect of fire's behavior, the upward movement of flame and smoke. You've likely noticed that flames always reach upward in Earth's gravitational field, and smoke from extinguished candles rises rather than falls or spreads horizontally. This predictable behavior reveals another set of physical principles at work, another language in which nature speaks to us, if we know how to listen. The upward movement of flame and smoke results from buoyancy, the tendency of less dense fluids to rise through more dense, surrounding fluids under the influence of gravity. When a flame heats the air around it, that air expands, becoming less dense than the cooler air farther from the flame. This creates a buoyant force that lifts the heated air upward. As this air rises, cooler air flows in from below to replace it, feeding the flame with fresh oxygen and perpetuating both the combustion and the convective flow. This vertical movement of air around a flame creates what scientists call a convection current, a circular pattern of flow driven by density differences. You can sometimes see this flow made visible in the wavering of a flame or the rising spiral of smoke. What you're witnessing is gravity's subtle choreography of fluid dynamics, a dance of density and temperature that connects the smallest candle to atmospheric processes spanning thousands of miles. Indeed, the same physical principles that drive the upward reach of a flame also drive global weather patterns. The uneven heating of Earth's surface by the sun creates temperature differences that lead to density differences in the atmosphere, generating winds and weather systems through essentially the same mechanisms that cause smoke to rise from a candle. From the flutter of a flame to the spin of a hurricane, from the rising thread of incense smoke to the global circulation, cells that distribute heat from equator to poles, all are manifestations of gravity acting on fluids of varying density. The smoke itself tells yet another story, and of combustion incomplete, of carbon particles too large to burn fully before escaping the flame's heat. These particles, carried aloft by convective currents, provide a visible trace of air's movement, much as dye dropped into water reveals currents otherwise invisible to the eye. In their spiraling, dissipating dance, we can read not just the flow of air, but also the transition from order to disorder that characterizes all natural processes. For most of human history, smoke rising into the sky served as a visual metaphor for the connection between earth and heaven, between the mundane and the transcendent. In traditions worldwide, from Native American ceremonies to Tibetan Buddhist rituals, from ancient Greek sacrifices to contemporary Catholic masses, smoke rising from flames has symbolized prayers, offerings, or spirits ascending to higher realms. The physical reality of buoyancy and convection became a powerful metaphor for spiritual aspiration, a tangible representation of humanity's reach toward the divine. The Lakota people speak of the smoke from their sacred pipes as carrying prayers directly to Wakantanka, the Great Spirit. As the aromatic smoke from tobacco and sacred herbs rises, it creates a visible bridge between worlds, a tangible manifestation of communion with the unseen. The very act of smoking the pipe is called Changnungpa Ichia, which translates roughly as to offer the pipe, suggesting that the smoke itself is the offering, the vehicle of connection. In Vedic traditions of ancient India, the sacred fire ritual called yajna similarly employed rising smoke as a medium of communication. The Sanskrit texts describe Agni, the fire, as the mouth of the gods, consuming offerings and transforming them into smoke that ascends to celestial realms. The Rig Veda, composed over 3,000 years ago, contains hymns addressing Agni as a deity who carries the oblation, conveying it to the gods. The physical phenomenon of smoke rising became the foundation for an entire cosmology of exchange between humans and deities. In Greek and Roman traditions, the quality of rising smoke from sacrificial fires was carefully observed for omens. Straight rising smoke suggested divine favor, while smoke that billowed or hugged the ground indicated rejection of the offering. The Latin term spiritus, from which we derive spirit, originally referred to breath or air in motion, connecting the immaterial essence of life to the visible movement of smoke. This etymological connection persists in many languages, linking breath, spirit, and rising vapor in a semantic cluster that points to ancient understandings of the soul as an ascending essence. Even in contemporary secular ceremonies, this symbolism persists. The Olympic flame, carried in solemn procession and ultimately raised high above the stadium, evokes this age-old association between ascending fire and transcendent human aspirations. The eternal flame at memorial sites, from Arlington National Cemetery to the Hiroshima Peace Memorial, suggests that something of the honored dead continues to rise upward, that their memory and significance transcend the physical remains, the candle-lighting ceremonies that mark countless religious and secular occasions, from the intimate glow of birthday candles to the solemn illumination of memorial candles, from the festive lights of Diwali to the sacred flames of Hanukkah, all draw on this primordial human fascination with fire as a medium of transformation, a visible manifestation of invisible realities. When we make a wish and blow out birthday candles, we participate in an ancient pattern of thought that sees in flame a connection between material and immaterial realms. This universal language of fire speaks to something fundamental in human experience, our recognition that we inhabit multiple dimensions of reality simultaneously, that the physical world we perceive with our senses exists alongside realms of meaning, value, and consciousness that cannot be directly observed but can be symbolically represented. The rising flame, with its base firmly in matter, yet its tip reaching toward immateriality, perfectly embodies this dual citizenship that defines the human condition, this capacity to derive meaning from natural phenomena, to see in physical processes reflections of our inner lives, is one of the defining characteristics of human consciousness. We are pattern seekers and meaning makers, constantly weaving connections between what we observe in the world and what we experience within. The upward reach of flame becomes aspiration. Its warm light becomes understanding. Its consumption of fuel becomes sacrifice or transformation. The physical world becomes a mirror for our consciousness, reflecting back to us the patterns of our own thought. Cognitive scientists have demonstrated that this meaning-making tendency emerges remarkably early in human development. By 6 months of age, infants begin to interpret the movements of simple geometric shapes in terms of intentions and goals, attributing agency to mere patterns of motion. The famous Heider-Zimmel animation, in which triangles and circles move in relation to each other, reliably elicits narratives about pursuit, hiding, aggression, and protection from viewers of all ages and cultures. We seem hardwired to perceive meaning and intention, to transform raw perception into narrative. This cognitive tendency extends beyond social perception into our relationship with the natural world. Anthropologist Stuart Guthrie has argued that anthropomorphism, the attribution of human characteristics to non-human entities, represents a fundamental cognitive strategy, an overdetection of patterns that resembles human agency. Though sometimes dismissed as primitive thinking, this tendency to see faces in clouds, to hear voices in the wind, to perceive intention in natural events, may have served important evolutionary functions, preparing our ancestors to detect predators and potential allies in ambiguous sensory data. The psychological term pareidolia describes this specific tendency to perceive meaningful patterns in random stimuli, seeing a face in the moon, hearing words in static, discerning figures in ink blots. Far from being a cognitive flaw, this pattern recognition capacity underlies much of human creativity and insight. Leonardo da Vinci advised artists to gaze at stained walls, clouds or muddy water to find inspiration for landscapes, battles and figures adorned with infinite things, the capacity to see what isn't literally there, to perceive potential patterns beyond the immediately given, fuels both artistic creation and scientific discovery. Poet and philosopher Samuel Taylor Coleridge described the imagination as the living power and prime agent of all human perception, distinguishing between the primary imagination, that structures, basic perception, and the secondary imagination that dissolves, diffuses, dissipates, in order to recreate. This creative dimension of perception transforms the flame's flickering dance into a metaphor for consciousness, its consumption of wax into an emblem of mortality, its warmth into the presence of love or understanding. We do not merely see the flame but read it, interpreting its physical properties as signs pointing beyond themselves. The cognitive linguist George Lakoff has demonstrated how metaphorical thinking structures not just poetry but everyday language and thought. We conceptualize time in terms of space, the future lies ahead. Understand quantity in terms of verticality, prices are rising, and frame emotional states in terms of physical orientation, I'm feeling down. These aren't merely linguistic flourishes, but fundamental cognitive frameworks that allow us to grasp abstract concepts through physical analogies. The flame that reaches upward becomes, through this metaphorical capacity, an image of striving, of transcendence, of enlightenment. This metaphorical thinking isn't limited to individual concepts, but extends to entire domains of understanding. Philosopher Mark Johnson speaks of image schemas, recurrent patterns in our sensory-motor experience that provide structure for conceptual understanding. The containment schema, derived from our experience of physical boundaries, shapes how we conceptualize categories and logical relationships. The path schema, based on physical movement, informs our understanding of purposeful action and narrative. The force schema, drawn from experiences of physical resistance, underlies concepts of causality, necessity, and compulsion. Through these embodied metaphors, our concrete physical experiences become the foundation for abstract thought. When we contemplate the flame, then we bring to bear these deeply ingrained patterns of metaphorical understanding. Its upward movement activates our verticality schema, associating it with positive valuation, increase, and transcendence. Its containment of energy within a defined form engages our containment schema, suggesting identity maintained through change. Its transformative consumption of fuel evokes the source path goal schema, implying purposeful process. The physical flame becomes a nexus of meaning, a focal point for multiple intersecting patterns of metaphorical understanding. This meaning-making capacity isn't merely imposed on the world from without, but often discerns genuine, structural parallels between physical processes and abstract realities. The flame's maintenance of form through continuous exchange of matter offers a genuine structural parallel to the maintenance of identity in living systems. Its sensitivity to environmental conditions mirrors the responsiveness of consciousness to context. Its emergence from underlying chemical processes reflects the emergence of mental states from neural activity. Our metaphorical readings of natural phenomena sometimes capture real isomorphisms between different levels of reality. Yet these metaphorical connections aren't merely arbitrary projections. They often reflect genuine structural similarities between different levels of reality. The branching pattern of a river delta resembles the branching of a tree, which resembles the branching of bronchial tubes in the lungs, which resembles the branching of neural pathways in the brain. These similar forms emerge in different contexts because they represent efficient solutions to similar problems of resource distribution. Whether those resources are water, sunlight, air, or information, the mathematical field of fractal geometry, pioneered by Benoit Mandelbrot, provides a language for describing these self-similar patterns that recur across different scales. The classic example of the Mandelbrot set reveals infinite complexity, with similar patterns emerging at ever-increasing levels of magnification. Natural systems frequently display similar properties. Coastlines maintain their characteristic irregularity, whether viewed from space or from a beach. Clouds show similar patterning at different scales. Mountain ranges display comparable structures from continental scale down to individual rocks. The fractal dimension of natural forms, a mathematical measure of how complexity changes with scale, often falls within surprisingly narrow ranges for diverse phenomena. The branching patterns of neurons, blood vessels, river systems, and lightning strikes all display fractal dimensions that optimize particular functional relationships between surface area and volume, between energy expenditure and distribution efficiency. These aren't coincidences, but reflect the emergence of similar solutions to similar physical constraints across vastly different contexts. Biologist Darcy Thompson, in his landmark work on growth and form, demonstrated how many biological shapes can be understood as mathematical transformations of similar underlying patterns. The spiral forms found in nautilus shells, hurricane formations, spiral galaxies, and the florets of sunflowers all approximate the logarithmic spiral, a form that maintains its shape as it grows. This equiangular spiral, described mathematically by Jacob, Bernoulli appears repeatedly in nature because it represents a growth pattern that adds material without changing the basic structure. A particularly efficient way of maintaining form through expansion, the Fibonacci sequence, where each number equals the sum of the two preceding numbers 1, 1, 2, 3, 5, 8. 30 appears with remarkable frequency in natural structures, from the spiral arrangement of leaves around a stem, maximizing sunlight exposure, to the branching patterns of trees, optimizing resource distribution. The related golden ratio, approximately 1.618, derived from the relationship between consecutive Fibonacci numbers, appears in structures as diverse as the proportions of the nautilus shell, the spiral arrangement of sunflower seeds, and the branching patterns of blood vessels. Network theorist Albert Laszlo Barabasi has demonstrated that many complex networks, from cellular metabolism to the World Wide Web, from ecological food webs to social networks, display scale-free properties, with similar patterns of connectivity appearing at different levels of organization. These networks tend to develop hub nodes with disproportionately many connections, creating efficient information or resource flow while maintaining resilience against random disruptions. The similarity in network architecture across diverse domains suggests fundamental organizational principles that transcend specific contexts. Systems theorist Stuart Kauffman speaks of order for free, the tendency of certain classes of complex systems to spontaneously generate ordered patterns without external direction. From the hexagonal cells of honeycomb to the spiraling patterns of hurricanes, from the synchronized flashing of fireflies to the coordinated movements of bird flocks, order emerges from the interaction of relatively simple components following local rules. These emergent patterns aren't imposed from outside, but arise from the inherent properties and relationships of the system's components. The flame exemplifies many of these natural patterns. Its characteristic shape represents a dynamic equilibrium between the upward force of heated gases and the constraints of diffusion and oxidation rates. The flickering patterns at its edges display chaotic dynamics, similar to those observed in weather systems, neural activity, and financial markets. Its ability to maintain consistent form, despite continuous replacement of its material components, parallels the persistence of biological organisms through metabolic turnover. These structural similarities aren't merely poetic analogies, but reflect genuine isomorphisms between different manifestations of natural pattern formation. In the same way, the behavior of fire captures something essential about all dynamic systems that maintain themselves through continuous energy flow, including living organisms and conscious minds. The flame's simultaneous stability and mutability, its existence as pattern rather than substance, its sensitivity to environmental conditions, all these qualities have parallels in the nature of consciousness itself. Perhaps this is why flames have served so effectively as metaphors for the mind throughout human cultural history. Heraclitus, the pre-Socratic philosopher known as the Obscure, found in fire the perfect metaphor for existence itself. His famous dictum that everything flows and panta rhei was coupled with the observation that all things are in exchange for fire, and fire for all things as goods for gold and gold for goods. For Heraclitus, fire epitomized the paradoxical nature of reality, simultaneously constant and changing, unified yet diverse, structured yet fluid. The flame's ability to maintain its form while continuously exchanging substance captured his vision of a cosmos governed by logos, rational pattern, within perpetual flux. Buddhist philosophical traditions developed sophisticated analyses of consciousness that emphasized its flame-like qualities. The Buddha himself employed the metaphor of a flame passed from one candle to another to illustrate the concept of rebirth without a permanent self, the continuation of pattern without the transfer of substance. Later Buddhist philosophers developed this analogy in the doctrine of momentariness, Kshanikavada, which held that consciousness, like a flame, consists of a series of discrete moments, each arising from and conditioning the next, creating the appearance of continuity through constant renewal. In Western philosophical traditions, John Locke compared personal identity to the continuous flame of a candle, maintaining its unity despite the constant replacement of its substance. Gottfried Wilhelm Leibniz extended this analogy, arguing that the mind, like a flame, represents a center of activity that continuously transforms its environment while maintaining its distinctive nature. The phenomenologist Edmund Husserl described consciousness as a streaming present, strömmende Gegenwart, a continuous process of becoming rather than a static state, evoking the dynamic flow of flame. Contemporary neuroscience increasingly understands consciousness in terms that parallel the dynamics of fire. The neural correlates of consciousness appear to involve not specific brain structures considered in isolation, but patterns of activity, rhythmic oscillations, synchronization, and information integration across distributed networks. Neuroscientist Gerald Edelman described consciousness as the remembered present, emphasizing its dynamic nature, its constant recreation through ongoing neural processes that maintain continuity through change. Much as a flame maintains its form through continuous combustion, the influential global workspace theory proposed by Bernard Baars and developed by Stanislas Dehaene envisions consciousness as a dynamic process whereby certain neural representations gain temporary dominance, becoming broadcast throughout the brain. This model echoes the flame's characteristics, a temporary pattern of energy flow, sustained through constant renewal, sensitive to conditions, maintaining coherence without stasis. The ignition of consciousness in this model involves a sudden nonlinear transition in neural activity patterns, reminiscent of the threshold dynamics of combustion. Philosopher Alva Noe argues that consciousness should be understood not as something that happens within us, but as something we do, a skillful engagement with the environment, a process rather than a state. This inactive approach emphasizes the dynamic, relational nature of consciousness, its existence at the interface between organism and world. Like a flame, which exists precisely at the boundary where fuel meets oxygen, consciousness in this view is neither simply inside nor outside, but emerges from the ongoing interaction between brain, body, and environment. The integrated information theory developed by Giulio Tononi proposes that consciousness corresponds to a system's capacity to integrate information measured by a value called phi, F. A system with high phi maintains a balance between differentiation, many possible states, and integration, unified functioning. Much as a flame maintains both complexity, in its detailed flickering patterns, and coherence in its overall structure. Both consciousness and flame represent organized energy flows that preserve form through constant material exchange, balanced at the edge between order and chaos. As the candle burns even lower, its flame perhaps guttering slightly as it nears the end of its fuel, let's consider another aspect of fire's behavior, its apparent unpredictability within overall patterns of consistency. Watch the flame closely for a moment. While it maintains a recognizable overall shape and behavior, the details of its movement seem to follow no fixed rule. It flickers and darts in ways that cannot be precisely predicted. Even while conforming to the broader constraints of physics, this combination of pattern and unpredictability exemplifies what scientists call deterministic chaos, systems that follow definite physical laws but remain fundamentally unpredictable in their specific behaviors due to extreme sensitivity to initial conditions. The mathematics of chaos theory, developed largely in the latter half of the 20th century, has transformed our understanding of complex systems, from weather patterns to economic fluctuations, from the rhythms of the heart to the dynamics of neural activity. The discovery of deterministic chaos challenged the Laplacian vision of a perfectly predictable universe, where sufficient knowledge of initial conditions would allow complete forecasting of future states. Pierre-Simon Laplace had famously suggested that an intelligence knowing all forces and positions of all particles in the universe would embrace in a single formula the movements of the greatest bodies of the universe and those of the lightest atom. For such an intelligence, nothing would be uncertain, and the future, as the past, would be present to its eyes. This vision of perfect determinism began to crumble with Henri Poincaré's work on the three-body problem in celestial mechanics. Poincaré discovered that even simple systems governed by Newtonian physics could display behaviors that were practically unpredictable due to extreme sensitivity to initial conditions. A minuscule difference in starting positions could lead to vastly different trajectories over time, rendering long-term prediction impossible even in principle. Given the inevitable limitations of measurement precision, Edward Lorenz, studying simplified models of atmospheric convection in the 1960s, rediscovered this principle and coined the term butterfly effect to describe how tiny perturbations could cascade into major differences in outcomes. His famous question, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" captures the essence of chaotic sensitivity. The mathematics of chaos theory reveals how simple deterministic equations can generate patterns of infinite complexity. Behaviors that appear random, but actually follow strict deterministic rules. A candle flame exhibits chaotic behavior because the tiny eddies and currents in the air around it can dramatically affect its shape and movement. A breath so faint you cannot feel it, a barely perceptible change in the room's temperature gradient, even the subtle air displacement caused by your own heartbeat, any of these can cascade into visible changes in the flame's dance. This exquisite sensitivity means that even if we could measure all relevant variables with perfect precision, which quantum uncertainty prevents, we still could not predict exactly how a real flame would flicker 10 seconds from now. Yet within this unpredictability, patterns emerge. The flame never transforms into a cube or suddenly burns green unless chemical additives are present. It maintains certain statistical properties, certain ranges of behavior, that define it as a flame rather than something else. This balance between constraint and freedom, between determinism and indeterminacy, characterizes many of the most interesting systems in our universe. The weather follows similar principles, governed by well-understood physical laws, but chaotically sensitive to initial conditions, making long-term specific predictions impossible while still allowing for reliable statistical forecasts. The famous butterfly effect describes how a butterfly flapping its wings in Brazil might, through a cascade of atmospheric interactions, eventually influence the formation of a tornado in Texas. The specific chain of cause and effect becomes too complex to track, even though each individual step follows deterministic physical laws. The mathematics of chaos reveals order within apparent disorder. When the behavior of chaotic systems is plotted in phase space, a mathematical representation of all possible states, striking patterns emerge. The strange attractors that characterize chaotic systems show how seemingly random behavior actually follows hidden patterns of remarkable complexity. The Lorentz attractor, resembling a butterfly's wings, shows how chaotic systems orbit around preferred states without ever exactly repeating their trajectories, creating patterns that are neither completely predictable nor completely random. Chaotic dynamics appear throughout nature, in the turbulent flow of fluids, in the irregular beating of hearts, in the fluctuations of animal populations, in the firing patterns of neurons. The ubiquity of chaos suggests that it represents not a flaw in nature's design, but an essential feature, perhaps even a creative principle. Chaos provides systems with adaptability, responsiveness, and the capacity for novel behavior, qualities essential for living systems navigating complex environments. Our brains and minds appear to operate according to similar principles. The approximately 86 billion neurons in a human brain form a network of staggering complexity, with each neuron connecting to thousands of others. This network exhibits both deterministic constraints, imposed by anatomy and biochemistry, and chaotic sensitivity, where tiny perturbations can cascade into significantly different neural states. From this balance of order and chaos emerges the phenomenon we experience as consciousness, consistent enough to maintain a sense of identity fluid enough to respond creatively to new situations. Neurologist Walter Freeman, studying the olfactory system of rabbits, discovered that their brain activity displays chaotic dynamics, deterministic patterns with sensitive dependence on initial conditions. When a rabbit encounters a new odor, its brain activity shifts from one chaotic attractor to another, representing a fundamental reorganization of neural activity rather than a simple input-output response. This chaotic behavior allows the brain to escape from established patterns, to create novel responses to novel situations, to learn and adapt rather than merely execute fixed programs. Subsequent research has revealed chaotic dynamics throughout the brain, from the firing patterns of individual neurons to the large-scale oscillations of neural populations. These chaotic patterns don't represent noise or dysfunction, but appear essential for healthy brain operation. Excessive order in neural activity, such as the abnormally synchronized firing observed in epileptic seizures, impairs normal function. Conversely, complete disorder would prevent coherent activity. The brain operates at what physicist Stuart Kauffman calls the edge of chaos, a state poised between rigid order and complete randomness, capable of both stability and innovation. This chaotic quality may be essential for the creative dimensions of consciousness. If neural activity followed entirely predictable patterns, how could novel thoughts emerge? If mental processes were completely determined by prior states, how could genuine insight or innovation occur? The chaotic dynamics of neural systems provide a physical basis for creativity, not as a violation of physical law, but as an expression of the intrinsic unpredictability of complex deterministic systems. Philosopher Daniel Dennett suggests that consciousness involves a form of multiple drafts, competing, neural patterns that vie for dominance in a continuous process of revision and selection. This model resonates with the chaotic dynamics of complex systems, where multiple possible trajectories compete before the system settles temporarily into one basin of attraction. Your next thought isn't predetermined in detail, but emerges from this dynamic competition, shaped by but not reducible to prior states. Neuroscientist Carl Friston has proposed that the brain operates according to active inference, continuously generating predictions about incoming sensory data and updating its internal models based on prediction errors. This process inherently involves chaotic dynamics, as tiny discrepancies between prediction and reality can cascade into significant reorganizations of neural activity. Like a flame responding to subtle air currents, consciousness maintains its coherence through continuous adaptation to changing conditions, a dynamic stability rather than a static state. This perspective suggests that the unpredictable flickering of a flame isn't an imperfection or a failure of physical law, but an expression of the intrinsic creativity of complex systems. The flame's dance, like the flow of your thoughts or the development of weather patterns, represents a form of natural improvisation, a continuous exploration of possibilities within constraints. There is freedom in this flux, a kind of liberty that exists not despite, but because of the lawful structure of reality. The implications for our understanding of free will are profound. If consciousness, like other chaotic systems, follows deterministic laws, yet remains unpredictable even in principle, then perhaps the ancient dichotomy between determinism and free will represents a false choice. Our decisions may be neither random nor completely predetermined, but emerge from chaotic dynamics, determined in the sense of following physical law, free in the sense of not being predictable or reducible to prior conditions. Like the flame's dance, our choices may represent a form of chaotic liberty, neither arbitrary nor compelled but creatively constrained. As you watch the candle flame, you might notice occasional larger fluctuations, perhaps a sudden brightening or a more dramatic shift in shape. These events often occur without obvious external cause, emerging from the internal dynamics of the flame itself. Such spontaneous variations exemplify what scientists call emergent behavior, properties or events that arise from the interactions of simpler components but cannot be predicted or explained by analyzing those components in isolation. Emergence appears throughout nature, from the crystalline patterns of snowflakes to the synchronized flashing of fireflies, from the murmurations of starling flocks to the collective intelligence of ant colonies. In each case, relatively simple individuals following local rules generate complex, coordinated group behaviors without centralized control. The whole becomes not merely the sum of its parts, but something qualitatively different, possessing properties that were not present in any of the constituent elements. The concept of emergence challenges both reductionism, the view that complex phenomena can be fully explained by breaking them down into simpler components, and vitalism, the view that living systems contain some non-physical vital force. Instead, emergence suggests that nature is organized hierarchically, with new principles, patterns, and causal powers appearing at different levels of complexity. These emergent properties aren't supernatural additions to physical reality, but arise naturally from particular configurations and interactions of physical components. Philosopher C.D. Broad, who helped develop the modern concept of emergence in the early 20th century, distinguished between resultant and emergent properties. Resultant properties, like the weight of a molecule, can be predicted by simply adding the properties of the components. Emergent properties, like the transparency of water or the consciousness of a brain, cannot be predicted or explained from component properties alone, but require understanding the specific organization and interactions of the system as a whole. The classic example of emergence is water. The properties of H2O, its liquidity at room temperature, its surface tension, its ability to dissolve many substances, its maximum density at 4 degrees, cannot be predicted from studying hydrogen and oxygen gases in isolation. These properties emerge from the specific ways that hydrogen and oxygen atoms bond to form molecules, and the ways these molecules interact with each other through hydrogen bonding. Nothing about the behavior of isolated hydrogen or oxygen atoms would lead one to predict the remarkable properties of water. Biological systems display emergence at multiple levels. The properties of proteins, their three-dimensional folding patterns, their catalytic abilities, their binding specificities, emerge from the specific sequences of amino acids and their interactions. The functions of cells, metabolism, reproduction, responsiveness, emerge from the organized interactions of thousands of different proteins and other molecules. The integrated behaviors of organs and organisms emerge from the coordinated activities of numerous cells. Each level exhibits properties and principles not present at lower levels. A flame, too, is an emergent phenomenon. None of the individual molecules of wax or oxygen knows about fire. None contains the property of luminous combustion. Yet when sufficient numbers of these molecules interact under appropriate conditions of temperature and pressure, the phenomenon we call flame emerges, a structured process with properties distinct from any of its components. The flame exemplifies what complexity theorist Stuart Kauffman calls order for free, the spontaneous emergence of organized patterns from the interactions of simpler components following local rules. The flame's characteristic shape, its consistent color gradients, its dynamic stability, these aren't designed or programmed, but emerge naturally from the underlying physics of combustion. The specific shape and behavior of the flame represent what physicists call a dissipative structure, a pattern that forms spontaneously in systems far from equilibrium, maintained by the continuous flow of energy through the system. This emergent quality of fire connects it conceptually to the phenomenon of consciousness, which many philosophers and scientists now view as an emergent property of neural systems. Just as flame emerges from the interactions of molecules without being reducible to any single molecule, consciousness may emerge from the interactions of neurons without being locatable in any single neuron. Both phenomena exist at a higher level of organization than their physical components, arising from pattern and process rather than from substance. The philosopher John Searle distinguishes between causal reduction and ontological reduction. While conscious experiences may be causally reducible to neural processes, in the sense that they are caused by and realized in brain activity, they may not be ontologically reducible in the sense that the subjective, first-person nature of experience cannot be eliminated or translated without remainder into third-person physical descriptions. Like the flame that is causally reducible to chemical reactions, Yet ontologically distinct as a macroscopic phenomenon, consciousness may be both physically realized and genuinely novel. This emergentist perspective offers a middle path between reductive materialism, which struggles to account for the subjective dimensions of consciousness, and dualism, which posits consciousness as a separate substance. Instead, it suggests that consciousness, like other emergent phenomena, arises naturally from particular configurations of physical processes, introducing genuine novelty without requiring non-physical substances or forces. The flame's emergence from chemical processes provides a visible analogue for this more subtle emergence of mind from brain. This perspective invites us to see the flame not as a thing, but as an event, a temporary pattern in the flow of energy through matter. The same carbon and hydrogen atoms that now participate in the candle's combustion have existed since the early universe and will continue to exist long after the flame is extinguished. What makes the flame a flame is not the specific atoms involved, but the pattern of their interaction, the structured process of their transformation. Similarly, what makes you may not be the specific atoms that currently comprise your body, which are completely replaced many times over a human lifetime, but rather the pattern of their organization, the structured process of their ongoing exchange with the environment. Like a flame, you exist as a pattern in the flow of matter and energy, a pattern far more complex and self-maintaining than a candle flame, to be sure, but perhaps different in degree rather than in kind. This process-oriented view of identity has deep roots in both Eastern and Western philosophical traditions. The pre-Socratic philosopher Heraclitus famously observed that no man ever steps in the same river twice, for it's not the same river and he's not the same man. Both river and man exist as processes rather than fixed entities, maintaining their identity through continuity of pattern rather than permanence of substance. The river's pattern persists, despite the constant replacement of its water. The man's pattern persists, despite the continuous renewal of his cells. The Buddhist tradition developed this insight into the doctrine of Anatman, or no self, the understanding that what we experience as a permanent, unchanging self is actually a continuous process of becoming, with no static essence to be found. The Buddha's famous fire sermon, Adita Pariyaya Sutta, uses the metaphor of flame to illustrate this point, describing how attachment to a permanently existing self generates suffering, just as fuel sustains a consuming fire. Liberation comes through recognizing the processual nature of existence, the continuous arising and passing away of all phenomena, including what we call self. Modern biology confirms this processual view of living systems. Your body replaces most of its constituent atoms over time. The atoms in your skin are replaced every few weeks, those in your liver every few months, even those in your bones every few years. What persists is not the substance, but the pattern, the organized process that continuously exchanges matter with the environment while maintaining its structure. Biologist Lynn Margulis described living organisms as not fixed things or entities, but shifting sets of relationships that endure through time and across space. Cognitive scientist Francisco Varela developed this insight into the concept of autopoiesis, the self-creating, self-maintaining process that defines living systems. An autopoietic system, like a cell, continuously produces the components and boundaries that constitute it, maintaining its identity through constant material exchange with the environment. This process-oriented view applies equally to multicellular organisms, to ecosystems, and perhaps to mental systems. All maintain their identity not through fixed substance, but through continuous self-regeneration. The flame exemplifies this processual nature of identity. It persists as a recognizable entity, despite the continuous replacement of its substance, because it maintains a specific pattern of energy flow, a structured relationship with its environment. Its identity isn't located in any particular atom or molecule, but in the organized process of combustion, the dynamic pattern that persists through continuous material exchange. In this sense, the flame isn't a thing that burns, but rather burning itself, a process temporarily localized in space and time. Similarly, your identity may be understood not as a fixed entity housed within your body, but as the ongoing process of embodied living, the organized activity of metabolism, Perception, cognition and action that maintains itself through continuous exchange with the environment. You are not a being that experiences, but rather experiencing itself, not a thing that lives but living itself. A process temporarily localized in a particular body with a particular history. This perspective on identity as pattern, rather than substance, has profound implications for how we understand ourselves and our place in the universe. If we are processes rather than things, events rather than objects, then the boundaries between self and other, between organism and environment, become more permeable than our everyday experience suggests. We are not separate from the flows of matter and energy that constitute the world, but particular configurations of those same flows, temporary eddies in the river of becoming. This processual view doesn't negate the reality of individual identity, but reconceives it in dynamic terms. Your particular pattern of organization, your genetic inheritance, your developmental history, your accumulated experiences and memories, remains uniquely yours even while continuously exchanging substance with the environment. Like a flame, you maintain distinctive characteristics, color, shape, movement, despite constant material flux, persisting as a recognizable entity while never remaining exactly the same from moment to moment. As the candle burns toward its conclusion, the flame sometimes grows smaller, its light diminishing as the available fuel dwindles. This gradual dimming reminds us that all fires, whether candle flames or stars, eventually exhaust their fuel and return to equilibrium with their surroundings. This return to balance isn't a failure but a fulfillment, the completion of a cycle that began with the concentration of potential energy and concludes with its dispersal. The second law of thermodynamics, which describes the inevitable increase of entropy in closed systems, is often misinterpreted as a principle of decay or degradation. But entropy isn't disorder in the colloquial sense. It's a measure of energy dispersion, of the spreading of energy across available states. The increase of entropy represents not chaos overcoming order, but energy finding its most probable distribution, like water flowing downhill to find its level. The Austrian physicist Ludwig Boltzmann, who developed the statistical understanding of entropy in the late 19th century, expressed this principle in his famous equation S K log W, where S represents entropy, K is Boltzmann's constant, and W represents the number of possible microscopic states corresponding to a given macroscopic state. This equation reveals that systems naturally evolve towards states that can be realized in more ways microscopically, not because they are disordered in any absolute sense, but because they are statistically more probable. Consider a simple example. When you drop a drop of blue dye into clear water, it gradually disperses until the entire volume becomes uniformly pale blue. This increase in entropy doesn't represent a loss of order in any absolute sense. The molecules of dye and water follow precise physical laws throughout the process. Rather, it reflects the astronomical number of possible arrangements in which the dye molecules are distributed throughout the water, compared to the relatively few arrangements in which they remain concentrated in one region. The system evolves toward higher entropy, not because order is being destroyed, but because the high entropy state can be realized in vastly more ways microscopically. The beauty of a candle flame lies partly in its temporary reversal of this entropic tendency. The concentration of energy in the flame creates a local decrease in entropy, a brief flourishing of organization amid the general flow toward energy dispersal. The flame can maintain this state only by continuously exporting entropy to its surroundings in the form of heat, light, and combustion products. Eventually, the available fuel is consumed, and the system returns to equilibrium. Physicist Ilya Prigogine, who won the Nobel Prize for his work on dissipative structures, demonstrated how systems far from equilibrium, like flames, living organisms, or weather systems, can spontaneously generate order by exporting entropy to their surroundings. These dissipative structures maintain their organization not by violating the second law, but by remaining open systems that exchange matter and energy with their environment. They represent not exceptions to the entropic tendency, but local manifestations of it, temporary eddies in the general flow toward equilibrium. Living organisms operate according to similar principles. As physicist Erwin Schrödinger observed in his influential book, What is Life?, organisms maintain their internal order by continuously extracting order from their environment in the form of low-entropy nutrients and releasing high-entropy waste products. They are, in his memorable phrase, feeding on negative entropy. Like flames, living systems exist as temporary islands of organization in the cosmic flow toward entropy increase, maintaining their structure not by violating the second law but by remaining open systems that exchange matter and energy with their surroundings. This perspective transforms our understanding of the relationship between order and entropy. Rather than opposing forces, they represent complementary aspects of a single process, the creative dispersal of energy across available states. Just as a river's flow creates temporary eddies and vortices, even as it moves toward the sea, the cosmic flow toward entropy creates temporary structures, stars, planets, ecosystems, organisms, civilizations, even as it moves toward equilibrium. These structures don't defy the entropic tendency, but express it in local temporary formations of remarkable complexity and beauty. This pattern, concentration, flourishing, dispersal, return, appears throughout nature. Stars form from the gravitational concentration of interstellar gas, shine through nuclear fusion that temporarily reverses the entropic flow, and eventually disperse their substance back to the cosmos. Living organisms develop through the concentration of matter and energy, maintain their organization through metabolism that exports entropy to the environment, and eventually return their components to the cycles of nature. Civilizations arise, flourish, and fade, their material and cultural achievements eventually returning to the Earth or being transformed into new configurations. In each case, what might appear as an ending from one perspective can be seen as a transformation or renewal from another. The atoms that comprised yesterday's candle flame are still present in the world today, participating in new configurations, new processes. The energy released in that combustion has dispersed into the environment, contributing infinitesimally to Earth's thermal balance. Nothing has been lost, merely changed in form. This perspective doesn't deny the reality of endings or the poignancy of impermanence. The specific flame that illuminated your reading last night is gone, never to return in exactly that configuration, but it invites us to see such endings as part of larger cycles of transformation, rather than as final cessations. In the words of the ancient Greek philosopher Heraclitus, "No man ever steps in the same river twice, for it's not the same river, and he's not the same man." Both the river and the man exist as processes of becoming, rather than as fixed entities. As the candle's flame diminishes further, perhaps flickering now in the pool of melted wax at the base, its light grows softer, more intimate. In this gentle illumination, consider how the great fires of the cosmos, the stars, follow a similar trajectory. Though on timescales that stagger human comprehension, our Sun, a middle-aged star currently about 4.6 billion years old, will continue to shine relatively steadily for another 5 billion years or so. During this main sequence phase of its life, it maintains a balance between the gravitational force pulling its mass inward and the outward pressure generated by nuclear fusion in its core. This balance allows for the stable conditions that make life on Earth possible. The process occurring in the Sun's core represents a more fundamental form of combustion than the chemical reactions in a candle flame. Where the candle flame involves the rearrangement of electrons in chemical bonds, stellar fusion involves the transformation of atomic nuclei themselves. Every second, the Sun converts about 600 million tons of hydrogen into 596 million tons of helium, with the remaining 4 million tons transformed into pure energy, according to Einstein's famous equation E = mc2. This energy, initially in the form of gamma rays, is gradually absorbed and re-emitted through the Sun's outer layers, eventually emerging as the visible light and heat that sustains life on Earth. This stellar alchemy takes place under extreme conditions, temperatures of about 15 million degrees Celsius and pressures more than 200 billion times Earth's atmospheric pressure. Under these conditions, protons overcome their mutual electromagnetic repulsion and approach closely enough for the strong nuclear force to bind them together, forming helium nuclei and releasing enormous energy in the process. This nuclear fusion represents nature's most efficient energy source, converting matter to energy with the efficiency that dwarfs chemical combustion. The sun's steady radiance belies the dramatic processes occurring within. The energy generated in the core takes between 10,000 and 170,000 years to reach the surface, as photons are repeatedly absorbed and re-emitted by the dense plasma. This energy transport occurs primarily through radiation in the inner portions of the sun and through convection in the outer portions, creating the visible granulation patterns on the solar surface. The sun's apparent solidity from Earth disguises its true nature as a roiling, churning ball of plasma, a dynamic structure maintained through continuous energy flow. Eventually, however, the hydrogen in the sun's core will be depleted, leaving behind a growing core of helium. With its main fuel source diminished, the core will contract under gravity's pull, heating up enough to trigger helium fusion while simultaneously causing the outer layers of the sun to expand dramatically. Our star will enter its red giant phase, swelling to a size that may engulf the orbits of Mercury and Venus, and perhaps even Earth. This expansion will be accompanied by increased luminosity but decreased surface temperature, shifting the sun's color from its current yellow-white to a deeper orange-red, not unlike the way a candle flame sometimes glows more redly as it nears extinction. The red giant phase will last perhaps 1 billion years, during which the sun will lose mass through stellar winds, shedding its outer layers into space. When the helium in the core is eventually exhausted, our sun, lacking the mass necessary to compress its core enough for the fusion of heavier elements, will shed its outer layers entirely, forming a planetary nebula, a luminous cloud of expelled gas illuminated by the hot core. This core, now exposed, will become a white dwarf, an Earth-sized remnant composed mostly of carbon and oxygen. Incredibly dense but no longer capable of fusion reactions, this white dwarf will gradually cool over trillions of years, its glow diminishing from white to yellow to red, and finally fading to the background temperature of the universe. What was once a mighty furnace converting 600 million tons of hydrogen to helium every second will become a cold, dark ember, a black dwarf theoretically. Though the universe isn't yet old enough for any white dwarfs to have completely cooled, more massive stars follow different evolutionary paths, potentially culminating in spectacular supernovae or collapsing into neutron stars or black holes. Stars with masses more than 8 times that of our Sun can fuse elements up to iron in their cores. Beyond iron, fusion no longer releases energy but requires it, leading to a catastrophic collapse of the core when its fusion fuel is exhausted. The outer layers of the star rebound from this collapse in a supernova explosion that, for a brief period, can outshine an entire galaxy. These stellar explosions are cosmic forges, creating and dispersing elements heavier than iron, including gold, platinum, uranium, and many others, throughout the interstellar medium. The dramatic phrase, "we are stardust," expresses a literal truth. The atoms of carbon, nitrogen, oxygen, and other elements that form our bodies were created in the hearts of stars that lived and died before our sun formed, their substance scattered through space by supernova explosions and stellar winds, eventually coalescing into the planets and, ultimately, into us. This cosmic recycling continues. The atoms in your body, temporarily organized into the pattern you recognize as yourself, will eventually disperse and recombine in new forms, perhaps as soil, as plants, as other creatures, and eventually, in the distant future, when Earth itself is reclaimed by the sun or dispersed into space, as components of new stars and planets. Your physical substance, like that of the candle flame, participates in cycles of transformation that extend across cosmic distances and timescales. When we contemplate these stellar life cycles, we're reminded that our sun, the source of nearly all the energy that powers life on Earth, the light by which we see our world, the warmth that makes our planet habitable, is itself a temporary phenomenon. Its seemingly eternal radiance is, on cosmic timescales, as fleeting as the flame of a candle in the night. Yet this impermanence doesn't diminish its significance. Rather, it connects our star to the universal patterns of becoming and transformation that characterize our dynamic universe. The candle before you may now be burning its last, the flame retreating closer to the remaining wax, its light growing softer. As it nears its conclusion, consider how this simple flame connects you to the cosmos, not metaphorically but literally. through unbroken chains of physical causation and shared fundamental principles. The carbon atoms in the candle wax may once have been part of ancient forests, their structures built through photosynthesis, powered by sunlight. Before that, these same atoms were forged in the hearts of stars that lived and died before our sun was born, scattered into the interstellar medium by stellar winds or supernova explosions. The oxygen that combines with this carbon in combustion has its own cosmic history, much of it generated by generations of photosynthetic organisms that gradually transformed Earth's atmosphere over billions of years. Every atom in your body has a similar cosmic history. The hydrogen in your cells, in water molecules, in DNA, in proteins, originated in the Big Bang itself, formed during the first 3 minutes of the universe's existence. The carbon that forms the backbone of your organic molecules, the calcium in your bones, the iron in your blood, the phosphorus in your DNA, all were created through nuclear fusion in stellar cores. The heavier elements in your body, iodine, selenium, zinc, required the extreme conditions of supernovae for their formation. Physicist Carl Sagan famously observed that we are made of star stuff, a poetic expression of this literal truth. Pure physical substance participated in the death throes of ancient stars, drifted through interstellar space for perhaps billions of years, coalesced into the solar nebula that formed our sun and planets, cycled through Earth's geological and biological systems, and now temporarily comprises your body. You are not merely connected to cosmic processes. You are a manifestation of them, a particular configuration in the ongoing dance of matter and energy that constitutes our universe. The heat from the flame warms your skin through the same mechanisms of radiation, convection, and conduction that distribute energy throughout the universe. The light enters your eyes through the same electromagnetic interactions that allow starlight to cross billions of light-years of space. The chemical reactions of combustion follow the same laws of thermodynamics that govern energy transformations from the quantum scale to the cosmic. Your very ability to perceive and understand the flame demonstrates another form of cosmic connection. The cognitive and neural processes that enable your consciousness evolved through billions of years of biological history, shaped by the same physical and chemical principles that govern all natural systems. The atoms that form your brain cells follow the same quantum rules as atoms throughout the universe. The electrical signals that carry information between neurons obey the same electromagnetic laws that govern lightning strikes and radio waves. Moreover, the conceptual categories through which you understand the world, space, time, causality, identity, relationship, evolved in response to the actual structure of reality. As philosopher Hilary Putnam observed, the mind and the world jointly make up the mind and the world. Your cognitive abilities aren't arbitrary constructions, but evolved capabilities that reflect, however imperfectly, the actual patterns and processes of the universe. When you recognize pattern and purpose in natural phenomena, you may be discerning genuine structures rather than merely projecting human categories onto neutral data. In observing this simple flame, you participate in a relationship with the cosmos that extends across vast reaches of space and time. Your awareness of the flame, your perception of its light and heat, your understanding of its nature, your aesthetic and emotional responses to its presence, represents a kind of cosmic self-reflection, the universe becoming conscious of itself through the medium of your embodied mind. The cosmos that produced the stars also produced you, not as something separate from natural processes, but as a particular manifestation of those same processes. The mathematics that describes the combustion of the candle flame also describes the neural activity that enables your perception of it. The laws of physics that govern the flame's behavior also govern the biochemical reactions that sustain your consciousness. The boundary between you and world reveals itself as conceptual rather than absolute, a useful distinction rather than an ontological divide. This perspective invites a sense of connection rather than separation, of participation rather than isolation. We are not observers of the cosmic drama, but expressions of it, not separate from the processes of nature, but particular manifestations of those same processes. The boundaries between in, here, and out there, between self and world, between subject and object, reveal themselves as conceptual rather than absolute, useful for certain purposes but ultimately permeable. This recognition doesn't diminish human uniqueness or significance, but contextualizes it within larger patterns. Just as a flame represents a particular kind of combustion process with distinctive characteristics, human consciousness represents a particular kind of cosmic process with its own distinctive features: self-awareness, symbolic thought, cultural, transmission of knowledge, ethical reasoning, aesthetic appreciation. These capacities aren't supernatural additions to the natural world, but emergent properties of particularly complex configurations of matter and energy, novel expressions of underlying cosmic principles. As the candle flame finally dims and fades, the thread of smoke rising briefly before dissipating into the surrounding air, there's a moment of transition. The structured dissipative system we've been observing reaches the end of its fuel supply and returns to thermal equilibrium with its environment. The visible flame disappears, but its effects persist. In the warmth added to the room, in the carbon dioxide and water vapor released to the air, in the transformed wax remaining in the candle holder, in your memory and understanding of what you've witnessed. This transition reminds us that endings are rarely absolute. The flame may be extinguished, but the components that constituted it continue to exist in new forms, participating in new processes. The energy released during combustion disperses, but is not destroyed. In accordance with the first law of thermodynamics, the carbon atoms that briefly glowed in incandescence may eventually be incorporated into new plants through photosynthesis, potentially becoming part of a future candle, or indeed part of your own body through the food you eat. This material, continuity amid formal transformation, characterizes all natural processes. Nothing in nature appears from nowhere or disappears into nothing. Everything transforms. The ancient Greek philosopher Parmenides expressed this principle in his famous dictum that what is cannot not be, and what is not cannot be, a philosophical anticipation of the modern scientific understanding of conservation laws. Matter and energy neither appear nor vanish, but continuously change form, maintaining quantitative invariance through qualitative transformation. The apparent emptiness left behind where the flame once flickered isn't truly empty. The space contains air molecules in constant motion, electromagnetic fields, perhaps subtle currents set in motion by the flame's heat. What appears as absence is actually teeming with activity, invisible but real, connecting this small region of space to the larger flows of matter and energy that constitute our world. As physicist John Wheeler observed, empty space is not empty. It represents a dynamic plenum rather than a void, a field of potential rather than a nullity. Similarly, what we perceive as endings in human experience often represent transformations rather than absolute cessations. The conclusion of a particular relationship doesn't erase the ways it has shaped us. The completion of a project doesn't eliminate its effects on our skills and understanding. The death of a loved one doesn't remove their influence from our lives. As T.S. Eliot wrote in Little Gidding, what we call the beginning is often the end, and to make an end is to make a beginning. The end is where we start from. This continuity amid change exemplifies a fundamental characteristic of our universe, what physicist David Bohm called the implicate order, a deeper connectivity underlying the apparent separateness of objects and events. From this perspective, distinct phenomena like flames, stars, or living organisms are manifestations of an underlying wholeness, temporary articulations of a continuous field of being. Their individual identities matter, but so do their connections to the larger patterns of which they are expressions. Bohm used the hologram as a metaphor for this implicate order. In a hologram, each part contains information about the whole. If you break a holographic plate, each fragment will still produce an image of the entire original scene, albeit with reduced resolution. Similarly, each phenomenon in nature contains traces of the larger whole of which it is an expression, connections to other phenomena that may not be immediately apparent, but that reflect an underlying unity. The flame that has now disappeared participated in multiple overlapping systems: the chemical system of combustion, the thermodynamic system of energy flow, the perceptual system of your observation, the conceptual system of your understanding. Its existence temporarily integrated these diverse domains, creating a nexus where different aspects of reality converged. Though the flame itself has vanished, the connections it momentarily embodied persist in transformed ways. As silence and darkness return to the room, allow yourself to rest in this sense of connection, this awareness of participating in processes that extend far beyond the boundaries of individual experience. The flame you've been observing may be extinguished, but the cosmic story it embodied continues, with you as both witness and participant. The ancient Greek philosopher Heraclitus, who found in fire the perfect metaphor for existence, famously observed that everything flows. This insight, that reality is process rather than substance, becoming rather than being, finds confirmation in contemporary understanding from quantum physics to systems theory, from cosmology to consciousness studies. The flame, in its dynamic impermanence, its structured yet ever-changing nature, captures this truth with elegant simplicity. At the quantum level, what appears as solid matter resolves into patterns of probability waves, distributions of potential rather than definite substances. Even the seemingly fundamental particles, electrons, quarks, photons, exhibit wave-particle duality, sometimes behaving as discrete entities, sometimes as extended fields. The particles themselves are better understood as excitations in quantum fields that permeate all space, temporary configurations in the underlying field rather than independent objects. As physicist Hans-Peter Dürr put it, matter is not made of matter. It represents dynamic process rather than static substance. At the cosmological scale, the universe itself appears fundamentally dynamic. Space and time emerge together in the Big Bang and continue to evolve, with space itself expanding, carrying galaxies apart like raisins in rising dough. The seemingly fixed stars are in constant motion, many of them pulsing, some ejecting material in stellar winds, all moving through the galaxy, while the galaxy itself moves through the local group. What appears as the fixed backdrop of existence represents ongoing process, continuous transformation, perpetual becoming. Between these extremes, at the human scale, we encounter the flowing processes of life, metabolism, growth, reproduction, decay, transformation. Living systems maintain their identity through constant material exchange with their environment, preserving pattern while continuously replacing substance. Ecosystem processes cycle materials through diverse organisms, transforming waste into resource, death into life. Geological processes build mountains and wear them down, create and destroy landforms, rearrange the face of the planet over time. Nothing in nature remains fixed. Everything flows. This processual nature of reality doesn't negate the existence of persistent patterns or the validity of identity through time. The flame maintains its recognizable form despite constant material replacement. The river remains identifiably itself despite the continuous flow of its water. You maintain your personal identity despite the ongoing replacement of your body's cells and the continuous flow of your conscious experience. These persistent patterns represent what process philosopher Alfred North Whitehead called societies, organized collections of events that maintain structural continuity amid continuous change. As you prepare for rest, carry with you this awareness of participation in the flowing patterns of existence. Like a flame, your consciousness flickers and dances, responds to subtle influences, maintains its pattern while continuously renewing its substance. Like a flame, you exist as a temporary focus of energy and organization in the broader currents of cosmic becoming. And like a flame, your existence illuminates a small portion of the universe, casting light that allows reality to be perceived in new ways. This recognition of kinship with the flame doesn't diminish human uniqueness, but contextualizes it within larger patterns. Your consciousness, unlike the flame, can reflect on itself, can conceptualize its own nature, can intentionally shape its development through choice and practice. These capacities represent not departures from natural process, but particularly complex manifestations of it. Emergent properties that introduce new dimensions of possibility into the cosmic unfolding. The stars will shine long after we are gone, their light crossing endless space. but tonight they shine here with you in silence. The same fundamental processes that illuminate distant galaxies have, for a brief time, taken the form of a simple candle flame in your presence. The same cosmic story that began billions of years ago continues to unfold in this quiet moment. May your evening be calm and your rest be deep, cradled in the gentle rhythms of our universe's endless becoming.